Hello, my name is Micah. Today, I'll be going over the first question of worksheet 11 and specifically going over a mini lecture on heaps. So heaps might be new to some of you all, so I'm going to go over a quick mini lecture. The motivating problem. Why do we need heaps? Formally, our motivating problem is that we need a container of elements where each element has a priority associated with it, and the order in which elements are served are based on that priority. And there are two ways to order those elements, from greatest to least and least to greatest. My example here is, let's say we have an ongoing to-do list, okay? That's my ongoing to-do list. Say I have 3 elements right now, but my mom said that there's going to be a lot more coming. She just doesn't know what she wants me to do yet. Let's say like dishes, 5 minutes, vacuuming, 20 minutes, cleaning my room, 10 minutes. I want to complete tasks based on the amount of time it takes to complete them. So that's this area right here, okay? Say I want to complete the tasks that take the most amount of time first. So in this case, I'm going to want to vacuum the house first, then I'm going to clean my room, then I'm going to do the dishes. Here are 2 approaches that come to mind based on what we've already learned in this class. The first approach is to find the max element after each task. In the beginning, I'm going to search for the task that takes the most amount of time. In this case, it's task 2, that takes 20 minutes. Next, I'm going to find the element that takes the most amount of time in the next one, and so on and so forth. However, the problem with this is this isn't as efficient as we can be. It takes O of n time to find the max. And that's just too slow. I want to be able to instantly get the tasks that I need to do on a rolling basis instantaneously. A second approach is to sort the list, then perform the tasks in the order that we sorted them in. Okay. However, recall that we add elements continuously. The problem here is that this approach is not dynamic. Specifically, adding tasks to the list takes O of n time. It's too slow. Okay, so we have our motivating problem, and we want to come up with a solution. So in this class, we have seen stacks, queues, and their underlying data structures were arrays. The next one that can solve this problem efficiently is called a heap. Okay, the heap invariant says that every node is blank than its children. For a min heap, every node is going to be less than its children, meaning that the top element is a minimum, okay? For a max heap, every node is greater than its children, which means that the top element is a maximum. I want you guys to take a moment to think back to our motivating problem. For an ongoing to-do list in which we want to perform tasks that take the most amount of time first, which one of these, A or B, should we do? Should we use a min heap or a max heap? You'll see that the answer is a max heap. This is because the top elements are the ones that take the most amount of time. They are the maximum, as we see here. And we perform tasks by just pulling off the top elements. And based on the heap invariant, we know that the elements being pulled off, the order in which they are pulled off, are based on whatever is the maximum element at the time. It turns out that heaps are super useful in shortest path algorithms. In theory, heaps are represented as complete binary search trees. However, in practice, heaps are represented as arrays representing binary search trees. And we'll see examples of this right now. Here's the basic interface for min PQs and max PQs, okay? So like stacks and queues, you can insert elements and get the size of the data structure. What's different is that now you can, depending on whether it's a min PQ or max PQ, you can get the smallest or the largest, or remove the smallest or remove the largest. And that's represented here. So let's go over some problems so that you guys get the basic idea. Given an array, heapify it such that after heapification, it represents a max heap. Like always, we're going to start with asking ourselves, what's the heap invariant? Every node is what than its children. And because we're using a max PQ, every node will be greater than their children. Okay, so we read this like a binary search tree, and it looks like this. So we read it like so: 5, 12, 64, 1, 37, 90, 91, 97. We need to perform what's called heapification, such that the heap invariant, as in step 1, is true, that every node is greater than its children. Currently, that's definitely not true. We can see that 5 is not greater than 12 nor 64. And so the heap invariant is not true in that case. There are two ways that we can heapify our array. The first way is by going in level order. Recall that level order means pretty much reading the tree from left to right, top to down, as if we were reading a book. And for each element, we bubble up. Such that the heap invariant is true. This fact will be proven more rigorously in lecture if it hasn't been done already, that this takes O of n log n time. The second method is a bit faster. It's going in reverse level order and bubbling down from bottom to up and right to left, like so. And for each element, we bubble down, here we bubble down, here we bubble down. Now in the next step, we're going to go over what that means to bubble down. This method takes O of n time. And so this is the faster approach that we're happy with. Okay, let's heapify this array together. So in step 2, we chose that reverse level order is going to be the most efficient way to do this. So we're going to start from the bottom. 97. Is 97 greater than its children? Yes, because it's the only child. The same goes for 91. The same goes for 97. The same goes for 37. All of these 4 nodes are greater than its children because they have no children. But is the case true for 1? We see that it is not. So we swap 1 and its greatest child, 97. As a quick check, is 1 greater than its children? 1 has no children, so we see that it is. Okay, now 64. We check 64. Is 64 greater than its children? We see that it is not, so we swap with the greatest child once again. We swap these 2. Okay, that's a quick check. Is 64 greater than its children? We see that it is because it has no children. Next, we check 12. Is 12 greater than its children? We see that it is not. We swap with the greatest child, so we swap 12 and 97. As a quick check, we see if 12 is greater than its children, we see that it is greater than 1. So we can move on. We move on to 5. Is 5 greater than its children? We see that it is not. So we swap with the greatest child. The greatest child in this case is 97. So we swap. As a quick check, we see is 5 greater than its children? We see that it is not. So we swap with the greatest child. So in this case, we swap with 37. Now we check one more time because 5 is bubbling down. Is 5 greater than its children? We see that it is because it has no children. So we are done. Since we are done, we can now convert this heapified array into its array form. So we read left to right in level order. And this is our answer. Now that we've discussed how to heapify an array, let's discuss how to properly delete an element from a heap. What is our heap invariant? In this case, every node is less than its children. Now that we've discussed what our heap invariant is, let's go with the procedure. First, we delete the element, and in its place is the lowest element, in this case, the 9. We swap that with the top, it takes its place. This is what our new heap looks like. And so all we have to do now is bubble down that top element. Is 9 less than all of its children? We see that it is not, so we swap with the lowest element. So we swap 9 and 1. Is 9 less than its children? We see that it is not, so we swap 9 and 2. We swap the lowest element again. Last check. Is 9 less than its children? We see that because it has no children, it must be true that it is less than its children. So we are done. Just a bit of runtime analysis. Let's analyze how long each step took. We see that deleting an element took constant time, swapping with the lowest element took constant time, and bubbling down took log n time. So the total runtime for deleting the minimum element from a min heap and also deleting the maximum element from a max heap is log n. We'll conclude this lesson with insertion of elements. So the basic procedure is as follows. We insert at the bottom and we swim up. So we start with the 6 and we see that there's nowhere to swim up to, so we're fine. Then we add a 5. Then we ask ourselves, is 5 less than 6? We see that it is, so we swap. Then we add a 4 to the end. We ask ourselves, is 4 less than 5? We see that it is, so we swap. We add a 3. We ask ourselves, is 3 less than 6? We see that it is, so we swap. Then we ask ourselves, is 3 less than 4? We see that it is, so we swap. Finally, we add the 2. We ask ourselves, is 2 less than 4? We see that it is, so we swap. Then we ask ourselves, we keep bubbling up 2. Is 2 less than 3? We see that it is, so we swap once again. And we're done. Now let's really quickly, to conclude, go over the runtime of this operation. Inserting at the bottom, for one insertion operation, inserting at the bottom is pretty fast. It's constant time. But swimming up takes at most the height of the tree. The height of the tree is log n, so this takes log n time. Okay, so the entire operation, takes log n time. To conclude, I think this would be a good chance to really quickly go over the runtimes of each of these operations as we proved or went through an example of in this worksheet. So insertion we saw takes O of log n time, or theta at log n time. Get max or get smallest, that's just getting the top element, and that is constant time. Then we have removing the max or removing the smallest, and we saw that that also takes log n time. Getting the size, of course, takes constant time. And then we also saw that building out the constructor, and we saw that the constructor takes n log n time, as we saw in C. Okay, I hope this lesson helped you all learn more about heaps as an underlying data structure for priority queues, which will be super important and essential for the rest of the class. If you have any other questions, feel free to email me at micahtyong@gmail.com. Thank you so much, and have a nice day.